Well, thanks everybody for inviting me to give this presentation today. I'm going to spend some time and try and explain to you the history of ALMA, why ALMA is here in the Atacama, what's so special about the Atacama that makes it a very important place for astronomical facilities. I'm going to explain how we built ALMA, because it's a very complex, high-tech machine, which would be very difficult to put together at 5,000 meters altura. I'm going to talk a little bit about the benefits of ALMA to Chile, both regionally and nationally. And then I'm also going to mention something about the science, the fantastic science we've been able to do over the past 10 years of our operations. And then I'm going to close with a little bit of insight into the future about where we're going with ALMA. So how do I progress my slides? Un momento. Okay, so the first question I'd like to address is, how did ALMA come into being? Oh, I have to progress the slides as well as my talk. Okay, so how did ALMA come to be? So the story actually begins over 3 decades ago. There were 3 completely separate projects going on in 3 different regions of the world. One in Japan, one in North America, and one in Europe. And they all had the same ambition, and that was to build a world-leading astronomy facility to do astronomy at submillimeter and millimeter wavelengths, to try and detect a part of the universe that had never really been detected in great detail before. That is the cold dust and gas that exists between the stars. At some point, thankfully, they all realized that they could do so much more if they banded together and formed a collaboration, an international collaboration. Now, that's, as many of you know, that's a very easy thing to say, but that's not a very easy thing to do. But through an awful lot of scientific diplomacy, they managed to pull together what is now known as the ALMA Partnership that built the ALMA facility. And that partnership was led by the National Radio Astronomy Observatory in the United States, the European Southern Observatory in Europe, who also have telescopes here in the Atacama in Cerro Paranal and to be in Cerro Amazonas, and also the National Astronomical Astronomical Observatory of Japan, supported by the Natural Institutes of Natural Sciences of the Japanese government. And on top of that, they also had collaborations within those regions. So it also involves in North America, Canada, in East Asia, Taiwan, and South Korea, and all of the 16 member nations of the European Southern Observatory. Most importantly, though, it's important to realize that Chile is a very important part of ALMA. It's our host country. And so it's plays a vital role in the success of ALMA. Today, the observatory, we operate 24 hours a day, 7 days a week, 52 weeks of the year, and we produce amazing science on a very regular basis. I have to say that our success today is very much a result of the fact that the ALMA partnership could be formed, and we bring the strengths of all those different nations to bear in operating the telescope every single day. So the next question I'd like to answer, or address, I should say, is why here in the Atacama? Well, I think the answer is obvious, and it's certainly it's obvious to many other facilities as well as ALMA. The reason we're here in the Atacama is the Atacama is very dry. And because it's very dry, it's free of clouds. And that is essential for looking at the universe. Importantly for ALMA, ALMA detects light at millimeter and submillimeter wavelengths, and those wavelengths are very easily absorbed by water. And so it's really important to an observatory like ALMA that it is above most of the water in the atmosphere. And so it's important to be as high up in the atmosphere as possible. And so because of that, you will find that the submillimeter observatories in the world, and there are not many, a handful, are always on the tops of mountains, or in one instance, they've been or flown in balloons, or even above the atmosphere. However, to build an instrument like a facility like ALMA, that would be prohibitively expensive to put on a plane or fly in a balloon. And so we're at the highest, one of the highest sites we could get. We need to be at a high site. And that is, as you see in this photograph, is at 5,000 meters altitude on the altiplano of the Andes and close to San Pedro de Atacama. One of the questions that people often ask is, why is it so dry here? And it's really a unique combination of three things. The very cold current from the Humboldt Current coming from the Antarctic, the Andes that protect us from the moist air that's on the east side of the Andes in places like the Amazon and in northern Argentina. And lastly, the fact that we have the coastal range where whatever moisture is in that air that comes from the oceans is deposited on the coast. So it's a unique combination which makes the Atacama a fantastic place to do astronomy. Okay. And just to prove the point that the Atacama is dry, not that many of you need to know that, to be convinced too hard, with too much difficulty about that, since you live here. This is, why is this video stopped? This is the Atacama from space. You can see it's very dry. And I have to say, we searched quite a lot of places in the Atacama to find the ideal place, but ultimately we settled on this large flat area called the Altiplano, near to Cerro Chatnanto, because it's a very large, widespread flat area, approximately 16 kilometers, 20 kilometers across. And that allows ALMA to not only have its telescopes grouped close together, but also spread out over 16 kilometers. And that infers a much larger range of capabilities than had ever been achieved before with a submillimeter telescope anywhere in the world. And that's going to be very important for some of the science that I show you later. But one of the challenges is that even though we're at this very high site in a very dry location, 5,000 meters is not a very good, easy place to work. Most of us like oxygen, and there's not much oxygen at 5,000 meters. And so the challenge was, how would we build such a complicated facility, high-tech facility, in such a place? Well, we set about building a support facility. It's known as the Operations Support Facility, at an altitude of around 3,000 meters. That enabled us. That is where everybody lives when they're at the observatory. It's also where we were able to put all the sophisticated pieces of ALMA together before we took them to 5,000 meters. And in the video, you can see the antennas being assembled. Those parts for the antennas came from Japan, from North America, and from Europe. There were 25 antennas from North America. There were 25 from Europe. And there were 16 brought from Japan, all assembled at the OSF. And along with all the other sophisticated electronics, that was all shipped to the OSF, where it was integrated and then into the telescopes and then taken to 5,000 meters. Now, each one of these antennas weighs about 100 tons, And that's not something that we can pick up with a forklift and just drive it to the high site. So we needed a special transporter, and we have two of them. One's called Otto, the other's called Lore. And they are unique. There's only two of them in the world. And they are designed solely to be able to move antennas from one location to another. In 2009, we were able to put the first antenna in location at 5,000 meters. And then 2 years later, we had enough antennas, 12, to actually begin doing science with the telescopes. And so our first science observations were made in 2011, 2012. So I've mentioned that we have 66 antennas. So how do we make all those antennas work together to produce the amazing pictures we have? Essentially, the important thing is the beauty of having more than one telescope is you can essentially make it, in our case, our 66 antennas can be placed as close as 150 meters apart. And so we have 66 antennas very close together. And that basically enables us to have an eye, an effective eye that can look at the universe. And that's a relatively small eye. And that small eye is analogous to having a short zoom lens on your cameras that many of you have. And when you have a short zoom lens, you can see a lot more sky than if you have a long focal length lens. With ALMA, we can spread those antennas out over 16 kilometers, so we can have an eye that's effectively 16 kilometers across. Well, analogous to the zoom lens, let's say you have a zoom lens that can go to 400 millimeters, that enables you to see more detail. And so the same with ALMA, the further we put the antennas apart, the more detail we can see. And that's a very important That's an important thing to keep in mind when we think about the science that ALMA can do. So that explains how we can get different detailed pictures. The other thing to appreciate is that each one of our 66 antennas has, it says here with only 8 fingers about 10 different detectors inside. Each one of those detectors works at a certain wavelength of light, or range of wavelength of light. And those coincide with the parts of the atmosphere that are actually transparent to some degree to millimeter radiation. Each one of those receivers, it was state-of-the-art in 2011. They're cooled to 4 degrees Kelvin, minus 269 Celsius, to make them very sensitive, because appreciate that the signals that we get from the universe are incredibly weak. Many of you have cell phones, and you are all worried about how strong the signal may be, how many bars you have on your cell phone. Well, imagine trying to receive a cell phone signal from Mars or Jupiter. It's going to be very weak. And that is the sort of strength of signal, or even less, that we deal with on a daily basis. So our detectors have to be very, very sensitive. Once we have the data, we amplify it so we can work with it. We convert it into digital data. Then we send it down an optic fiber to a very special supercomputer that you see here in the picture. This supercomputer was the fastest computer in the world in 2011. It can do 10 billion calculations every second. It only does 2 things. It manages to multiply and it can add, but it does it very, very quickly. And then once we have the data go through the correlator that combines the data from the 66 antennas, we then send that data to our processing software that generates the amazing pictures that you get to see from ALMA. And perhaps, well, certainly they're the most detailed pictures we've ever seen at these wavelengths. And so to illustrate the kinds of pictures that we generate, here's a picture taken by the Very Large Telescope on Cerro Paranal. It's a picture of the antennae galaxies. And what you see in this image is all the hot material in this galaxy. They're the bright regions. They're mostly the stars. The stars look either white, blue, or red, and those colors tell us something about the temperature of those stars. You can also see in this image, you can see some of this dusty material. It's dust because it obscures the light from behind. All the light from the stars behind that dust is absorbed. And that dust is important when I show you the next slide, which is the ALMA data, the first ever science observation that we did with ALMA. You will see that it coincides very closely with all that dust. It will also coincide with the stars, which is also a clue as to what role the ALMA plays in detecting the cold dust and gas. So here is the ALMA image. Whoops. Here's the ALMA image of the same object, and you can see that the bright ALMA emission coincides with hot clusters, particularly the center of this galaxy. One of the galaxies here, it's actually two galaxies, this colliding, and then another center down here. And you can see that there's awful lot of ALMA emission that ALMA detects coming from those two regions. You can also see that there's emission in these areas associated with the cold dust that we know from the fact it absorbs the starlight. And so we can say, we certainly can see from this picture readily that it's highly likely that these very bright star clusters come from within the large dusty and cold, dusty, gaseous clouds in this pair of galaxies. So the important thing to take away from this slide is that ALMA is really very good at detecting the cold, dust and gas that lies predominantly between the stars and is also the locations of where stars are formed. So we're going to change gears slightly. We're going to come back to science in a few slides, but I just want to change gears and sort of try and highlight what are being the benefits of having a facility like ALMA here in the Atacama. And I have to say they are quite numerous. At ALMA we have 250 staff, más o menos, of which 220 are Chilean, and that includes engineers, it includes scientists, it includes technicians, and other very highly specialized professionals who keep our telescope systems working day in, day out, and help ensure that we can keep on observing 24/7. It's also important to realize that with those complex high-tech systems, we are always looking at ways of improving them and make the system work much better. And so not only are our staff very good at fixing things to keep them working, they're also very good at pushing things to make them work even better than they have done over the previous years. And so we're always pushing the capabilities of our staff and improving their skills through advancing the observatory on a daily basis. There is another benefit to Chile in that ALMA, like all the other telescopes here in the country, there is 10% of our time, our observing time, is guaranteed to be used only by Chilean astronomers at the Chilean universities. And so that access to world-leading facilities has really promoted a big growth in the Chilean astronomical community, which has seen enormous growth over the last 30 or so years, primarily through having large facilities, ALMA, ESO, here in the Atacama, and others here in the Atacama. And so that is also something that the country benefits from. I have to say that Chile now produces scientific publications at a rate very similar to other leading astronomy scientific nations, I should say. So that's a significant change in the last 20, 30 years. Locally, in the Antofagasta region, the observatory supports many different local initiatives through a special fund that we contribute every year that's administered by Region Antofagasta. This funding has supported many different local initiatives, particularly in socioeconomic development in the San Pedro de Atacama area, certainly I think over the last 15 years. One emblematic project that's been very successful for us has been the support of the science program at the local school in Tocanau, which is the community closest to the observatory. And Tocanau, the school there, is now one of the top 100 science programs in the country. And one of their students recently has taken up an astronomy degree at one of the universities here in Chile. So we're seeing direct benefits from that regional funding. So I'm going to go back to science. I'm going to share with you some of the things that we have done over the last 10 years, some of the amazing observations that we've made. And I like to think, I hope I can impress upon you what a game changer some of these observations represent. And so I'm going to touch on some of those highlights, but I want you to appreciate these are just highlights. I have to say it's remarkable to me as the director of the observatory, and having been a director at another observatory in the past, we produce press releases on a remarkable basis to describe the amazing science we do. It's certainly weekly that we have something exciting to share with the rest of the world. It's truly remarkable. And so I encourage you all to look at our website. Its website is almaobservatory.org. So you can see the many different types of results for yourselves. But I'm going to just touch on three highlights. And I really want to highlight the case of protoplanetary systems. These are the precursors of planetary systems like our own solar system. And it's really important that we study these in some detail. As Viviana Guzman was saying in one of the sessions earlier today, that really understanding these systems provides us with great insight into trying to understand better our own origins, how our solar system came to be, how come we have life here on Earth in particular, which are fundamental questions that we're all keen to know the answers of. And I'm going to say that ALMA has been a game changer, largely through this image you see here. It really helps inform us how our own solar system came into being 5 billion years ago. This is an object called HL Tau. I'm not going to ask you to remember that name. I have to say this image exceeds all expectations because of the detail that it shows. You can see structures here. You can see circles of bright orange. Well, it looks bright and orange in this picture. We can make it bright and blue if you wish. But those represent dust lanes or gas lanes. And the important thing is we see gaps between those structures. And those gaps are, some people think, due to planets forming and basically hoovering up all the dust and gas in those particular orbits around the parent star. This image has really challenged our ideas about how planets like our own Earth, Jupiter, Saturn, how planets form. And it's really helped narrow down the types of explanations. And I want to show to you just what a game changer ALMA is. So this is a state-of-the-art image from 10 years ago. This was the very best we could do looking at protoplanetary systems. On the left, you have HL Tau, and on the right, you have another system which is well-studied called TW Hydra. And this is what we could do 10 years ago. And I want you to draw your attention to the white circles in the lower left. Those denote essentially the level of detail you can pick out in these images. And I want you to note that there aren't too many white circles before it can be used to actually draw the diameter of those images. This is what ALMA did. Okay, and I want you to look at the white circles in the lower left now. That is the power of ALMA. It is the reason why 3 regions of the world clubbed together to build ALMA. That is a tremendous amount of detail that gives us access to science that just was not accessible even 10 years ago. And it really has changed the way we see how we look at planet formation and the formation of planetary systems similar to our own solar system. This has been key, and it's now become, I have to say, quite a predominant part of what we do. Here's one of the many large projects we've done. We've now studied many different protoplanetary systems. They come in different shapes and sizes, but I want you to note all of them show structure. Quite often it's symmetric, sometimes it isn't. There's a great variety of structures we see, but we see that things like gaps and rings are ubiquitous, okay? And that's really important in trying to understand where we come from. We now have lots of data, and we're certainly, the community is working hard on trying to understand how planets come to be. Okay. Another really important area for ALMA has been in the area of spectroscopy. It's really to try and advance our understanding of chemistry in space, and really trying to look at the question of where do atoms and where do molecules come from? What are the environments? How do they evolve within those environments to go from very simple structures, very simple atoms like carbon monoxide, for example, to very complex systems like sugars and other more advanced, more complicated molecular structures. So here is an example. This is a molecular cloud. I won't tell you its name, but the image, the somewhat messy image that you see is deuterium and carbon sulfide. And the structure in that image belies the mechanisms through which those molecules form. But importantly, at the bottom of this image, here you see a spectra. And that really is a fingerprint of all the different molecules that exist in this cloud. And I can tell you there are 15 different molecules here that we've identified, all based around the elements of carbon, nitrogen, oxygen, and most fundamental, hydrogen. We know that that atomic material comes from the centers of stars, clearly. We know also today that those elements were formed in the very early universe, from the first stars in the universe, because we now detect them almost at the very edge of the universe. And so it's clear that we get to, over time, remember the universe is 13 billion years old, over time we get to see the growth of very complex materials. And I'm going to tell you that the important molecule that we've detected in this spectrum, of which there are many things we don't know what they are, and it requires a lot more work to fully understand this spectrum, and this is just one of many that we've taken. We find this very relatively simple molecule. It's called glycolaldehyde, and it's a very simple sugar. But really the really exciting thing about this, it's a simple sugar, and we know that sugars are fundamental to more complex structures such as DNA. And so we're seeing hints of how essential building blocks of life are formed out in space. And I know I cannot leave Antofagasta without talking about black holes. I have one on my T-shirt. A very important experiment in ALMA's life, a very enigmatic experiment, to try and image a black hole. That's a very easy thing to say. It's a very difficult thing to do. There was a large collaboration of teams from all over the world trying to do that. And using 8 telescopes in different parts of the world, here in Chile, 2, Apex and ALMA on the Altiplano. In Hawaii, another 2. In France and in the South Pole and in Mexico, used together to form an eye, effectively the size of the Earth, to be able to resolve what a black hole looked like. ALMA was vital to the success of this experiment. To look at the black hole in M87, and I'm going to show you, this is M87. These images are fairly well known. It's a very bright radio source, but no one had actually seen down into the center of it, and the EHT managed to produce this image of this black hole. It's actually the shadow of a black hole. The black hole is in there somewhere. We can't see it because it's black, which means no light gets out. It's so massive that even light can't escape from its gravitational field. But what you see, all this bright emission here, is actually the hot material around the outside of the black hole. And effectively what we're looking at is the shadow of the black hole. This required ALMA because of our sensitivity. We're by far the most sensitive telescope in the world, and you need a lot of sensitivity to do this kind of experiment, because to be able to combine the data from telescopes so far apart it takes a lot of sensitivity to be able to calibrate the data, to calibrate it well. Okay. So today, we now have images of 2 black holes. One on the left is M87, and the other one is Sagittarius A star, which is the black hole in the center of the Milky Way. And one of the things that's really neat about this comparison is that the size of the objects is really interesting. They're almost identical, yet one of them is 1,000 times further away. And we can therefore determine that the relative mass of these 2 objects is approximately 1,000 times different. The black hole on the left weighs about has a mass of about 6.5 billion times the mass of the Sun, and the one on the right is 1,000 times less than that. So, those are the science highlights I wanted to share. Lastly, I want to say something very briefly about where we're going with ALMA. The important thing is to keep ALMA at the forefront of astrophysical research into the future. And over the next decade, we are going to expand the capabilities of the telescope such that we can observe 5 times faster with the full bandwidth of the telescope, and we're going to be able to detect about 100 times more spectral lines than we can today in any given instant. We're going to do that by replacing the detectors that we put in each of the antennas. We're going to make them have a bandwidth that's at least twice what it is today, ideally 4 times. A new digital transmission system. We're going to have a new correlator that is it's going to be so much better than the one we have today. That's one of the beauties about technology. It advances at quite a pace. And so in the 15 years since the current correlator was designed, electronics, particularly chip design, has really progressed. And so the capabilities of the new correlator are going to be just outstanding. And then, of course, we have to have an archive system and all the data processing software to handle the data. We are very excited about this prospect because it really is going to keep ALMA at the forefront of astrophysical research. And so we have much closer synergy with the latest instruments that are going to be coming with telescopes like the James Webb Space Telescope or the extremely large telescope that is being built on Cerro Amazonas at this moment. So it's really a very exciting future for us, and we're very excited about it. So what are we going to be able to do? What is the science that we're going to do? Well, with 5 times more sensitivity for some types of observations, 100 times more spectral lines, it really does open up the science we can do tremendously. We're going to be able to detect the very first stars and galaxies and understand their origin and the foundations of the galaxies that we see today. We're going to be able to study the origins of complex molecules through detecting more lines than we can today, which is really going to change our ability to dig into fields such as astrochemistry. It's going to get more complicated to understand. And then lastly, we're going to have more resolution. We're hoping to have antennas on longer baselines to be able to understand the detail of the protoplanetary systems on a scale that's much more similar to the Earth-Sun distance than we can do today. So those are our key science drivers for the next 10 years. I have to say that we're all incredibly proud of what we've achieved over the first 10 years of operations. We've changed the field, a number of fields dramatically, so we're approaching them in a somewhat different direction than we were before. And the future really, the future of the partnership and what we have planned to build over the course of the next 5 to 10 years is very exciting in terms of the science that we will be able to do with the new upgrade. So thank you for paying attention. Thanks for your time. I'm hoping you're going to follow ALMA and support us on the tremendous journey we're going to continue making over the next 10 years. Thank you very much.